Hello everyone, welcome back. So, till now we looked at several schemes including the compact scheme on how to basically discretize a system to approximate certain derivative. It may be the first derivative, second derivative, third derivative, and we saw that by intelligently using the implicit nature of basically implicit behavior of the derivative across the grid point, you can get high order accuracy using the compact scheme, right. But in all these examples, we assumed that the spacing between the 2 points are constant, right. So, that those kind of meshes are called the uniform mesh. So, for example, let us say if this is my grid. So, I have said that this is I plus 1, I plus 2, I plus 3 and similarly I minus 1, I minus 2, wherever you go the difference always is h, this is all h, right. Now, what happens that in many cases if you just want to use uniform mesh, the grid size that is required will be enormously large. For example, let us say if you want to solve flow over a flat plate. So, let us say this is my flat plate and I want to solve the flow over this. You make a domain like this, right. So, this is a flow. I mean, you can approximate, for example, what happens in the wind tunnel. There is a plate which is kept at the bottom, flow is coming from here, right. And if you have done any fluid mechanics course, you know that because of no slip condition, the flow will start basically it will have no slip on the wall. So, the velocity goes to 0 and it will basically start developing like this is the boundary layer that we have. Okay. This is the edge of the boundary layer. So, the boundary layer develops, that means the velocity is 0 here, let us say any point on the wall, and then as you go up this you will have nature like this, right. So, you will have 0 velocity and then velocity increases, and let us say this is 99% of the velocity, that is the edge of the boundary layer, right. So, what you note here is that most of the activities, your domain may be big, like this is your domain size, but most of the activities are happening close to the, I mean they are basically very close to the boundary layer, right. So, what you need to have is that you need to have very fine grid points very close to the boundary layer, but if you go away you might make a coarse grid like this, because there are not many things happening, your domain may be big. So, you have to make sure that there is no reflection coming from the top, right, otherwise it will impact the flow which is happening on the plate, right. So, and very close to the wall, I mean you have the boundaries should be basically the first grid point height should be very close to the wall, right. So, this y plus is something that you often use in a turbulent flow, it should be less than 1, right, typically, right. So, because you want to resolve the boundary layer behavior, right. So, what you can see here is that non-uniform mesh is a requirement. By that mean is that we want very fine mesh close to the boundary layer, very close to the wall, but away from the wall we may live with the coarse mesh, because there is not much activity happening there, there is no generation of vorticity there, right. There is no change of velocity, drastic change in velocity there, right. So, this is a kind of uniform flow there, right. If you do not use the non-uniform mesh, what will happen that whatever grid size that you are using at the bottom, let us say the first wall point, okay, first point next to the wall, you will have to use the same delta h, delta y or h everywhere. So, the number of grid points will increase a lot, right, because that typically that delta y is very small number, right. So, in fact, if you do this kind of solution, you may see that your delta y based on I mean depending on the length scale and of course, the velocity, it may be order of 10 power minus 5 minus 6 meter, and here you can go to let us say 10 power minus 3 or 10 power minus 2 meter away from the wall, right. So, you need a domain so that there is no spurious wave coming from the top or maybe from the right, but at the same time you need to make sure that your grid is refined well enough near the wall, right. So, in these cases and most of the cases that you would see in the practical situations, wherever there is a wall you need to have non-uniform mesh, right. So, how do you basically calculate the derivative in the non-uniform mesh, because as you know that so very close to the wall, let us say this is my wall and the first point height is let us say h, but next I made it coarse. So, this is actually called the boundary layer meshing. You start with the first layer height, then you use some stretching ratio which can be let us say 1.1 or 1.2 or something like that. So, that if it is h, this is 1.1 h, then next will be 1.1 square h, right. So, basically this is the geometric way, and there are many other ways to basically increasing the grid size, right. So, the derivative formula will be different in this, different in this and different in this, right. So, how do you calculate that? That is one thing, especially if you are using a finite difference approach. Secondly, we also, I mean, the another approach that we do is we use something called the curvilinear transformation. So, what is the curvilinear transformation does? I will not go into the detail here, but maybe I will discuss later in later classes, right. So, you may have very non-uniform mesh here, but this is let us say x and y coordinate, and we will transform it to something called zeta eta coordinate. So, this is my zeta and this is eta, which has got basically uniform meshing everywhere, okay. But then this x, zeta eta are related to x and y by some derivative j, which basically takes the derivative of the distances of x y to zeta eta. Right. So, that is another approach, but right now just look at how we can calculate the derivative if the mesh is non-uniform, right. So, to give an example, so let us say I have these two meshes, okay, this is I plus 1 and this is I minus 1, and sorry, I should have actually made little bit further, okay, so that you would note that okay, my delta x. So, this is let us say I minus 1, right. So, this is my delta x I plus 1 and this is my delta x I minus 1, right. So, they are not equal, that is what it means, right. So, I have defined this is called delta x I, which is x I minus 1, and this is delta x I plus 1, which is delta x I plus 1 minus, sorry, x I plus 1 minus x I, right. And our task is similar to what we had earlier. We want to find out what the derivative at I. So, du by dx at I. Okay. So, let us do that. So, what we need to do now? We need to have basically two Taylor series like we have been doing earlier. So, u I plus 1 and u I minus 1, but the one change that we have is here is that it is not h, the h is different in both the things. So, when you are doing u I plus 1, you are talking about x I plus 1 minus x I, right. So, that will be delta x I plus 1, and then whatever difference you have square by 2 u I double prime cube by factorial 3 u I triple prime and so on and so forth. Similarly, do u I minus 1. So, now the difference is I and I minus 1, so which is delta x I minus delta x I, which is x I minus 1, right. So, now since it is so you can write it as u x I minus delta x I, correct, and that is how you are basically doing the Taylor expansion. This was u x I plus delta x I plus 1, correct. So, you do that, and now like we had done earlier, you basically subtract this u I plus 1 minus u I minus 1, because we want to basically remove this term u I. So, this will go away, and finally, we will have these terms will be added, okay, and these terms will be cancelled, sorry, these terms will not be cancelled. So, if it were a uniform mesh, this delta x I plus 1 would have been equal to delta x I, and this would have been cancelled, right, but now it will not be cancelled, and similarly you can have this third term and so on and so forth, right. And what is this delta x I plus 1 plus delta x I? So, now basically we want to get this derivative. So, you take this on the left hand side and divide this thing to all of them, right. So, this is now delta x I plus 1 plus delta x I, which is nothing but this is x I plus 1 minus x I plus this one is x I minus 1, right. So, this will get cancelled out, you will have basically x I plus 1 minus x I minus 1, right. So, this will be x I plus 1 minus x I minus 1, and you can take this a square minus b square, that will be a plus b and a minus b. So, this a plus b will cancel out, will have this delta xi plus 1 minus delta xi by 2 ui double prime, right. So, one thing you can immediately note here is that because the grid was non-uniform, we could not cancel these terms, and that becomes our leading order term here, right. So, even though we are using 3 stencil point I plus 1 and I minus 1, because the mesh is non-uniform, your first error term or the leading truncation term, this is first order, this is ui double prime, but this is of the order of h, right. So, earlier we had the second order accuracy when we had this uniform mesh, when all these things were h, right. Imagine that then my delta x I is equal to h, I plus 1 is equal to h and delta x is equal to h, this term will cancel out, right. So, the next order term will be h square, which is what we saw in the central differentiation scheme, right. But because the mesh is non-uniform, these terms are not equal, and that is why this becomes your leading order term. So, your order of accuracy decreases. Now, it is just the first order accurate, the derivative of second order, but it is the first order accurate, that is in the leading edge term, right. So, this is how you will calculate the first order term, the first derivative, okay, and this is your error. So, the leading truncation is order of delta x, this is the first order accurate axiom, right. Now, if you want to make it, you want to see the what will happen if the mesh is uniform, that means this term will go to 0 and then this will disappear and you will get the term which is like this, and this is the second order accurate term, right. This is second order accurate, right. So, what we learned from it is just if you use a non-uniform mesh instead of a uniform mesh, even if you use the same scheme, the order of accuracy goes down when you use on a non-uniform mesh, right, for the same scheme. So, the non-uniform mesh leads to loss of accuracy for the same numerical scheme, right. Now, it depends I mean how much is the difference here. So, if the delta x I plus 1 is very close to, like let us say my delta x I plus, let us say small term delta, then error is not the first order term is not very big, the error is not very big, but let us say this is very different and this delta term is very large, right. So, then you will have very large error, and that is why when you do CFD, it is advised to you that you should not have very large jump between the two grid points. So, it should not be that one is like this and another is like this. If a very large jump, you can immediately see from here is that your error will be very high, right. If on the other hand, when you have gradual jump very small, so let us say delta xi and then you use delta small one, then you get delta xi plus 1, then add delta and so on and so forth, then your error is smaller, right. So, even if when you are using a non-uniform meshing, what you can basically ensure is that the jumps are not very large, right. So, typically it is handled in the finite difference either using this kind of non-uniform formula, mesh formula, or you can use the curvilinear coordinate system. When it is finite volume, we will see that anyway it depends on only on the left and the right state, okay. So, you do not have to go through this, you do not have basically information of I minus 2, I plus 2 and so on and so forth typically in the finite volume, especially when you are using the unstructured grid. Structured grid you can still use the same formulation that we have, right. So, this is a brief introduction about how this non-uniform schemes are derived for the non-uniform mesh. Now, what we will do, so we have basically got enough information about how we can approximate the derivative. Now, let us solve some model problems. So, when I say model problems, what we want to do is basically we will start with a simple linear convection equation. We have already seen those convection equations earlier, and then we will apply these derivative formulas, okay, the numerical approximations of the derivatives, and see how they behave, whether we are able to get what we are expecting, right. So, let us simulate some model equations, right. So, first is the linear convection, right. So, you can write the linear convection like this. So, what it means is that you give any profile, let us say my profile is like this, okay, and it is getting convected at a speed of c, right. And we saw that these schemes basically reveal a hyperbolic characteristics. So, it has a certain direction, it has got a characteristic. If you are using the second order, they will have two characteristic, right. So, if you the speed is let us say 0.5, then it will go to let us say 0.5 here, okay. If it is 0 and 1 and c is 0.5, so in 1 and you are using t equal to 1, so it will go like this, okay. And similarly, if you go to next time step, it will become like this, right. So, basically it is moving on the right without any loss of the diffusion, right. So, that is not getting diffused, there is no diffusion term here, okay. It is pure convection, right. Now, this it is a PD, the u depends on both time and the distance, right. So, you have to basically use the partial derivative term, and you need basically the discretization for both the time derivative as well as the spatial derivative. So, for the time derivative it is more easy because the time is always positive. So, if you make a sketch like this, so this is let us say your x here, okay, this is your x, and if certain distribution of u in the x, and let us say this is your time, correct. So, x is usually represented by I, and if it is x y I j, if it is x y g, then I j k, and time is usually represented by n, right. So, if you want to get this, so you have to get the derivative. So, if you are at I, you can use the forward differencing, you can use the backward differencing, you can use the central differencing, you can use the first order, second order, third order, fourth order, you can use compact scheme. So, basically for a given u, you have to get the term du by dx everywhere at a given I. Once you do that, so let us say, let me break this equation, that will be del u by del t is equal to minus c du by dx, del u by del x. So, let us say you got all this del u by del x you by using your favorite scheme, multiply by minus c, okay, that will be right hand side. Now, we have to use a scheme to basically march in time. So, what is your goal? We want to get, so for a given, this is called, so your u at n equal to 0 is given. So, initial condition is given, this is the initial condition at n equal to 0, that will be always be given, right. And then, so this is n equal to 0, you want to get to n equal to 1, right. So, here a very simple minded approach will be use the forward differencing. So, if you have du by dt, so you can write it as u n plus 1 minus u n by delta t. Just like we for the space we had du by dx is equal to u I plus 1 minus u I by delta x, that is the forward differencing, right. Similarly, you can write for the time. One more thing you may note that now that we have both space and time, I am using for the space, I am using the indices below the actual variable, and for the time we are using the superscript, you see n plus 1 and n. So, that if I want to use both of them, so you can write u I n, right, or u I plus 1 n, or u I n plus 1, right, or u I plus 1 n plus 1, whatever it is. So, basically at a given time and space I can describe using this notation, right. So, this you can easily do. If you know this value, you can write it as u n plus 1 minus u n by delta t is equal to minus c du by dx, which you can calculate using your favorite approach, and then you just multiply this thing with c and add the previous time. So, if you want to go to the first time step, so this will be like u 1 minus u 0 by delta t is equal to minus c du by dx, let us say it is known. So, u 1 will be u 0 minus c du by dx into delta t, correct. Now, you got the value at 1, so you got the value here. Now, you go to 2, now you go to 3, now you go to 4, and you can go to nth time step, whatever the maximum time that you want to go, right. So, this is how it is usually done. So, for now we have finalized the time stepping here. So, we are using a simple time marching. So, u n plus 1 minus u n by delta t, right. The tougher task is how to finalize the spatial scheme here, right. So, you can use the forward differencing. So, if you want to approximate du by dx to get the derivative, you want to go the forward differencing, that will be u I plus 1 minus u I by delta x. If you use the backward differentiating, that will be u I minus u I minus 1 by delta x. Same thing, if you use the central differentiating, it will be u I plus 1 u I minus 1 by delta x. Okay, let us limit up to let us say maximum 3 stencil. You can also write the formula for the 5th stencil, 4th stencil and so on and so forth. Now, even if you use just 2 stencil, which one you should choose, this one or this one, right, and how do you choose? Okay, and what if you use the central differentiating, right? So, for now let us choose this backward differentiating. Okay, I will tell you why, but let us say you choose this backward differentiating del u by del x equal to u I minus 1 by delta x. Okay, so once you do that, your formula will become like this. Okay, so let me just derive, I mean let me do it for you. Or maybe I will just do it here. Okay, so let me write it here. This du by dt is, I am writing both I and n now. So, this is u I n plus 1 at a given I. What is the difference in time by delta t, that is the approximate du by dt, and then you write plus c, and then I am using the backward differentiating as I told you. So, this b d is backward differentiating, f d is forward in time. The c is constant, and I am giving the constant convection speed, then this will become u I, and then it is given time n minus u I minus 1 at n by delta x is equal to 0, right. So, then you want to go to n plus 1 from n, the u I is known at every I in n. So, u I minus u I n is known, u I minus 1 n is known. Okay. So, you can write u I n plus 1 is equal to, you take this u I n on the right hand side, okay, and then it will come minus c delta t by delta x, and this term which is u I n minus u I minus 1 n, right. So, this is the formula which is what I have written here, right. Now, the next question is, how do you determine the delta x and delta t, right? Will it work for any arbitrary delta x or delta t, right? So, these are the questions that we need to answer, right. So, we will look into these things in the next class, but one thing I want to basically introduce here before I finish this class, that there is something called lambda or the CFL number, or also called the Courant number, okay, which relates the time step to the spatial spacing. So, L lambda is equal to basically c delta t by del x, and it actually puts the limit of what is the I mean how you can basically march in time with respect to given spacing, right. So, they are basically related, the delta t and delta x both are related, they are not independent, and this number is a very famous number in CFD. Okay, this is called the CFL number, or this CFL is I mean it is for initials of 3 scientists, Courant, Fredericks and Levy, okay, and sometimes it is also called the Courant number, okay. And because we are solving the convection equation, we have this is the convection or convective Courant number or convective CFL number. Similarly, we will have something called the diffusive CFL number, okay. So, in the next class we are going to solve these equations, okay, and basically we will see how to choose the delta x, delta t, and when it is stable, not stable, whether we are getting the right solution or not. So, let us meet in the next class. Thank you very much.